let's just do a quick review. The time evolved state, you apply the kinetic energy, the time evolution operator, for reasons even I'm not sure about. So we're evolving at a macroscopic amount of time from T naught, which is T, and again, that could very well be, that's still a short amount of time. Make no mistake, it's still a short amount of time. I'll let me get it door. Numbers are kind of loud. This, T0 versus T would still be like 2 to the minus 17 seconds, so don't make that mistake, it's still short. Anyway, so that's how you evolve a state. Last time we were doing this, actually what were we doing? Oh yeah, so we were doing various operators. Here, sorry, I'll do it this way. And looking at how things time evolved. Actually, is that right? Yeah, that's what we were doing. And what we found was, let's say, I think we did it this way. So if your state is a single state of the Hamiltonian, okay, so notice what I've done is I said state A is a eigenket of the Hamiltonian. I just stated that. And this state is the same, then there's no time dependence to anything. Nothing is changing in time. And that is evaluated by this. So of course we have to do an inner product, and we need to take the absolute square to know what the observables are. And while e to the minus I energy delta t over h bar appears in the time evolving state, the absolute value squared will get rid of it. So that's why that happens. And that's true. Sorry, I'm using does or does not. What do you call? Say work with. Okay, so maybe the operator, maybe A is an eigenket of the operator, maybe it's not. It doesn't matter. In either case, it doesn't time evolve. Okay, but if alpha is, whoops. Yeah, notice I'm speaking off the cuff. And I think I used the letter M last time. Okay, if the state is actually a sum of eigenstates in the Hamiltonian, then there is time dependence to everything. Okay. So again, the big lesson that we got out of that, and I'm going to do an example before we barrel off into the harder thing, is that if, like on the exam, I know I asked a time-dependent question on the exam, but I did that because we've already gotten all our Dirac notation down to deal with it. We just have to do it. So to some degree, you had a little bit of a preview on the exam, but again, you should have been able to do it. Okay, so a Hamiltonian is a field in the z direction, and you apply a plus state, a z plus state, nothing happens. You could ask about what is the spin in the z direction. Well, it's plus h bar over 2 and nothing happens. You could ask what is the polarization in the x direction. Now, plus is not the eigenket of SZ, yet nothing happens over time. Still 0. Okay, but if you apply the Sx plus state to a Sz Hamiltonian, it does evolve in time. Now, I know that's like, what, I'm going to write all that down. I'm just telling you, this is what I'm going to cover for about the next 10 minutes. That a superposition of eigenstates of the Hamiltonian evolve in time, but singular ones don't. And as I ended last time, I mentioned to you that the thing that's nutty about this is that you think of the ground state of the Hamiltonian, the ground state of molecules is, that's what mostly things are, right? Okay, I've got some light shining on my skin, so my skin molecules are getting excited, but for the most part, I'm assuming my molecules are in a ground state. Yet that has to be demonstrably false in a massive way, because then I wouldn't be moving, talking, I wouldn't even be warm, I'd be at 0 degrees. And yet none of that's true. So what you get from this is that basically nothing in the entire universe is in the ground state of the Hamiltonian. Nothing, except frozen crystals at 0 degrees K, and there's really not many of those just lying around anywhere. Maybe in the deepest regions of space away from all other stars, there's an H atom by itself that's not moving, and that's it. That's the only thing in the entire universe that's in a ground state of the Hamiltonian. Nothing else is. Everything is in a superposition state. And as I mentioned, this will come up at the end of the class, for H atom, if H atoms are doing things, and they are doing things. You know, the time of the position momentum uncertainty principle says that things are moving. Well, that's something. We think of the 1s state as the ground state, but I'm telling you, it's probably got some 2s or maybe some 2p, x, y, z, or all. It's got a little bit of that. It's got a little weight of that, or it can't move. So that's kind of the astounding thing that hopefully you get out of this. Now I mentioned to some of you on the way back to the SES, one of the reasons that is because when you take a really advanced quantum mechanics class like quantum 2 time, I had a whole class on time-dependent quantum, and what you learn is that the Hamiltonian of the hydrogen atom, which is just Coulomb's law, right? Just kinetic energy plus Coulomb's, that's the potential. You learn that that's actually not complete. There's other terms. Any of you ever heard of quantum electrodynamics? This is like what physicists who study people who study black holes and the Big Bang, that's what they study. It turns out that there is a part of a Hamiltonian that we will never put into our Hamiltonian, but there is a part of a Hamiltonian involving light that should be in every Hamiltonian that we write down. Again, it's way complicated, I'm not going to do it. But that extra Hamiltonian means that a 1s state of a hydrogen is not the ground state. That's the ground state for the Hamiltonian we use, but it's not, excuse my language, but it's not God's Hamiltonian, right? And that's the right one. Not that I'm religious or anything, but just saying, I think you get my point. Anyway, that's why that works. I can tell you a little bit more some other time, maybe during an extra session, but again, it's a little bit outside of the field of the class. Okay, for an example, let's do an example, and also recall, because this is going to be important, we are using the Schrodinger frame where states evolve in time. You don't need to write that down. We're going to be doing the Heisenberg picture later for the same problem. The problem we're going to do is an electron in the same problem we've been doing over and over and over and over and over again. We're still going to do an electron in the magnetic field. Right? Stern-Gerlach. But now we're going to let it evolve in time. Okay, so the moment, and I have to admit, I think I'm forgetting something here. Anyway, I got this from the book. I think there's the G factor is missing. Anyway, charge of the electron, mass, speed of light, so therefore this is connected to the theory of relativity in some way. Remember, you never see the speed of light unless the theory of relativity has some effect here. I don't know what that means beyond what I just said. And notice that this is the spin. That's the result of the spin operator. So the fact that electrons have an inherent spin is what makes them magnetic. Remember, that's also refrigerator magnet type magnetism. versus NMR magnetism, which is from a nucleus, which is like 1,000 times or 2,000 times weaker. Okay, let's make a Hamiltonian by putting an electron in a magnetic field like we've been doing over and over again. And okay, so the moment times the magnetic field, right? So again, maybe I never remember this stuff. It's basic EMF physics, freshman year, right? Moment times E field vector. Anyway, okay. Now let's make it. The field has, it's a Tesla or something, whatever that is. I think a Tesla is like a hell of a lot. So there we go. So we've decided that the dot product here, the magnet is pointed up down. So there you go. Relatively straightforward. Okay. Now, let me point out. Okay, so clearly SZ in the Hamiltonian commute because the Hamiltonian is a function of SZ. And of course that means that the Hamiltonian has plus minuses kets. Again, this was on your exam. I'm not going to put this in matrix form again. If you want to have if you look at the answer key, I can walk you through it if you need to hear it in words tomorrow. No problem. I really try to help someone who wants to do that. It's okay if you don't. But of course, that means they're kettivation. That means you should know that there's no off-diagonal elements. And based on what we covered last time, I know this is still kind of swimming in your head. It means that these things can't evolve in time. Nothing I will measure, SZ or SX, will evolve in time. Okay. So anyway, so there's that. Okay. All right. Now here's a trick. So this is a notational trick. So don't think that I'm actually deriving anything. It's just I'm trying to make things easier. If I apply the Hamiltonian to the plus minus state, you end up with minus plus h bar over 2. That's coming from the minus sign here, which apparently, if you look up magnetism in general, it's Q over mc, but the charge of an electron is minus. So anyway, so you get a sign reversal here. Same deal I just wrote. Okay, so again, it's a state, and we're going to call this E plus minus. Okay, just some notation. Okay, here's the trick. Again, please don't think I'm deriving anything. I'm not. If I take the energy difference and you divide it by h, you should know that that's the frequency. From the frequency, sometimes physicists will present optical spectroscopy just on frequency, sometimes angular frequency, sometimes wave number, sometimes EV. Chemists, we like to use nanometers, worst possible thing we could have ever had, because nanometers is inversely related to energy. Anyway, just pointing that out. So anyway, difference of energy. This would be an absorption, right? Because that's final state minus initial state. If this thing's absorbing light, it's going to go from the initial state to the final state, but of course we reverse that final minus initial. H is the translation between energy and time. So this is frequency. Frequency, I can then figure out the energy, whatever units. Actually, that's it right there. Okay. Okay. Now here's the damnedest thing, though. All right. You know what that is? Angular frequency. And I fix that by making that h bar. Okay. And I notice I did a bunch of stuff, but it just gets my goat that a lot of times in science you see a derivation, someone says frequency, but they mean angular frequency. I mean, you can't get that wrong. 2 pi times energy is gigantic. It is a gigantic difference if it's not clear what you're talking about. Anyway, that always pisses me off. They'll say, so you'll see this. They'll say, oh, this is the frequency. It's the angular frequency. It is not the frequency. Those are distinct things. Anyway, so I always try to be really careful about this. And if you work through the units, so the point of this is that you get this, and that allows me to simplify the Hamiltonian like this. It's just way the heck better. Okay, so therefore, now the time evolution operator, again, U, because we like to emphasize how it's unitary. And that, of course, and now the book also, I'm following the book here. The book drops this whole T minus T naught. Yeah, the book drops this at this point. It just uses the letter T, which I appreciate. It's a little weird, but just assume T naught is 0, right? And it's nice of them to be careful enough to include it at the beginning, but eventually it gets tedious. Okay, now what that means is, and again, this is all straightforward. You know, on the exam, I was testing you on the last question, which again was kind of devastating. That's why most grades were pretty low with that one question. Well, what are you going to do? You know, if I reduce points from that last question, then they have to go somewhere else, and so you get devastated by different questions. Really, if you know what the Hamiltonian operator does on this, and this is a function of the Hamiltonian, and this is what I was asking. Do you know to just simply, write e to the, you know, the function of the eigenvalue. So again, we had done that a zillion times. So again, the plus state is an eigenstate of the time evolution operator, because that's just a number at this point, right? And that also, just to reemphasize again that if I then do this, so when I look at this, let's say I ask you to explain in words, this evolves the state in time, and this sees whether it's changing. You know, you are changing over time, and I'm trying to see how you relate to your former self, right? Now, again, the experiment yields this, and the experiment yields this, and what you should see here is, of course, plus plus, right? Because this is a number. If I draw this way, this just pops out of the way. It's just a number. And the complex conjugate, of course, that's still 1. It just chooses to be 1. Remember, I told you I proved this. Okay, so that's the complex conjugate. And then, of course, we get the non-complex conjugate. Look at that, it's the number 1. So nothing changes over time. All right. So again, this was a very long period of time to say nothing. And to some degree, remember, this is just saying, is your normalization changing over time? That's another way to interpret this. Does the normalization constant change over time? Absolutely not. So again, multiple interpretations of the same thing. I'm certain the normalization doesn't change over time. Okay, if you folks don't mind, let me wipe this out, because again, you know, I've been saying this over and over again, but I really like to emphasize it. Eigenstates of the Hamiltonian don't do anything. So nothing is the eigenstate of the Hamiltonian, but again, that's for another class. All right, so now let's make a superposition state. So again, I deleted it, but when you have a state that is composed of more than one eigenstate of the Hamiltonian, that's what we call a superposition state. And whenever you see any YouTube videos on quantum computing, that's like the thing they try to express to regular people, is that these superposition states are how you do quantum computing. And again, from our perspective, that's plus state plus the minus state. That's the hydrogen atom having one s character and a little 2p or something like that. Okay, in this case, what we'll do is all right, so we're time evolving, but we're going to do Sx plus. Now, Sx plus, of course, is the plus state plus the minus state, right? So that's a superposition state. And so we all know, again, I'm just picking it because it's convenient that it's this plus. Notice I gave myself some room. So I just like the fact that I can, you know, be on somewhat familiar ground and still have a superposition state. But don't forget this. That's a 2, by the way. Remember, the H bar is in the angular frequency. And yeah, notice that one's plus, one's minus, right? One's with the field, the other's against. Again, it's not an H bar, that's a 2. Okay, so, all right, so what? Now, we will, sorry. You didn't write anything wrong. Okay, so now what I'm going to do is time evolving. And I want to see how it changes with respect to its former self. Over time, are you still you? I probably have a good way to check that. Do some kind of stern girl on something. Actually, we have these things, ion cyclotron resonances, a type of mass spec. What you do, these things are huge. They're like propane cylinders. You know what I mean? Like outside the house, they're the size of hippopotamuses. Okay, what's inside of them is an ion. So you shoot an ion like a mass spec, and the thing is big because it's a magnetic field. It's actually an NMR turned on its side. What happens is the ions start moving in a circle. The magnetic field is strong enough that, again, a moving charge has a torque, and the torque is strong enough to cause it to spin. Then it gets trapped in there. And then what you can do is measure the speed at which the thing is rotating, and then you can get the mass that way. Totally forgot why I'm talking. So I don't know why I'm talking about that. Anyway, okay, so yeah, are you your former self? I totally forgot why I went off on that. And of course, we have to make sure that we have to calculate something that we actually measure, or it's kind of stupid. Okay. All right, what is this? Now notice the subtlety here. Don't mess this up. I am not. There's no e to the blah 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 factors here. Right? Oh, that bothers me. Didn't look good. There we go. That looks good. Okay. There's the bra. Make sure that you can see that. And here's the ket. And this does. Plus. Again, we've already kind of written the same thing again. It's kind of stupid. Okay. Go through it. What do you get? Again, I always hope you folks appreciate your notation, because look how, if you go through that, again, that at this point should be unbelievably trivial for you to do this. And it's trivial because of Dirac notation. You may notice something that looks a lot like e to the ix plus e to the minus ix, which I would recognize as cosine. So I recognize the interior as cosine, and then just square it. So not hard. Okay, now a lot makes sense here. I can imagine why cosine squared versus cosine. Well, cosine squared is never negative. Cosine can be negative. but an observable, the square modulus of something would be kind of hard to imagine why it would be negative. Plus, I'm asking, are you your former self? Why would that ever be negative? The worst thing you can be is a different person, which would be a 0. I have nothing to do with myself. That's as far away from yourself as you can be, but that would logically be a 0. So I get why it's squared. And a cosine, okay, what's cosine of times 0? 1, right? So I am myself at the beginning, but over time I will become something else. It makes perfect sense. In fact, go through this process for the minus state, assuming that you start with the plus state, and guess what? You get the sign. And you should be able to do that if you want to make sure you know what you're doing. Look at that. So that's where it becomes. And yeah, there you go. So again, now you can see a little bit about how time dependent works. I have to admit, I do sometimes get a little cross-eyed about remembering how, again, we did what happens to the plus minus state, the pure state, and nothing happens. It's only when you get superposition states do these things change. And this, of course, is what quantum computing, the idea of quantum computing is that you're making these measurements. You can use these things to do extra calculations is the idea. Okay, now last bit. I'll leave this up here. I'll do as much as I can here. This was just asking how the state changes, but now let's do a measurement. And this is maybe why I was talking about ion cyclotrons. Let's do this. What am I doing? Yeah, let's do. Okay, so remember, I just asked, does the state change? But I didn't actually measure anything. I mean, it's cool that I understand what's under the hood. That's what I got out of this. But I didn't actually make a measurement. I'm going to understand the measurement. I'm doing this one second because it's going to be a little bit easier to understand. Okay, so that's the question. So let's remind ourselves that SX. And I'm going to use the that formula that you saw a long time ago, where you expand. You have an outer product. Remember that term? This is an outer product. Outer product for operators times our eigenvalue. Sum of all states. That's an operator. So there you go. And now what I'm going to do is I am going to ask this question. I'm going to ask, what is the spin state? Sorry. How does the spin state change over time? Okay, now before, notice I've done something fundamentally different other than operating, other than having an actual Stern-Gerlach device thrown into the mathematics. Here, I'm evolving a state over time and just seeing whether it matches, whether it conforms to its former self, and the answer is yes and no, up and down over time. Here, I'm actually evolving both, if I had both of these being time dependent, the answer is 1. That's just checking whether the normalization changes, which it doesn't. Here, I'm evolving both states, but now I've got, now I'm asking an actual question. It wouldn't make sense if these were not the same thing. That doesn't really make any sense. Notice that the U operator, I'm assuming it's already been applied. So this is really U transpose S U. That's what's really going on. I'm just assuming that you know that. All right. Okay, what you get is h bar over 2 Sx plus, I know that looks Sx plus. That's coming from here, by the way. Okay, so again, time evolving here, Sx plus there. Notice that I've actually worked that out here in part. I've worked out a lot of that mathematics here. So that's why I'm not going to go through such detail here. I don't need to. Not time evolving. Time evolving. I know that my pluses and t's look the same. I'm trying not to. I guarantee I'm trying not to confuse myself. Okay, same deal. So what I'm doing here, I'm looking at my own notes and I have to admit I'm like, wait, what am I doing? It doesn't help that I'm getting these from the book. I just looked at this and I realized that this is flipped over from this, and I realized what I'm doing is a complex conjugate. Or that's what the book's doing, which I'm capable of using. And it looks like I'm gonna okay, so anyway, I flipped that term over. And it's not hard to see that this is what have I done? What have I done? Sorry, I'm not being careful with this, okay, so I make, yeah, this adds up, yeah, okay. Sorry, I did a little bump myself. Again, because there's two terms there, I can convert one into the complex conjugate. Identical except for being a complex conjugate. Right here, little beep beep. Let me pull it up. That thing go beep beep? No, it's still recording. It's still recording? Okay. I heard something go beep beep. Okay. All right, now, again, you guys, can you see this? Okay, so this ends up being cosine squared minus, all right, no need for an absolute value anymore. You don't need the absolute value because cosine squared and sine squared can't be zero. Can't be negative, sorry. All right, again, I have to admit, I'm still a little bit mixed here how this is happening. These seem to have gotten switched. You see the mean here, so you see how this is from the SX operator, but they seem to be switched here. So I may have made a mistake. Or it kind of just doesn't matter because you can rearrange things as complex conjugates. I'll look into this, but I have a feeling that this is an error. I think this is evolving in time, and that's evolving in time. Anyway, I think I've reversed them, but again, it actually wouldn't matter. So sorry about that. I'll double check that. That bothers me now. I should have noticed that before. That's what I do. I usually spend about an hour reviewing my notes. Because I'll see things like that, and I'm like, wait a minute, I don't understand that. Typically, I just have to make sure I understand it, and then I'm like, oh, yeah, wait, that's because of this. And again, though, because this is the second time I taught this class, it could be true that my notes are wrong. I've seen that happen a couple of times. So let me just point out that there's this thing called some of you might know this. What is it called? A half angle formula? I think that's what it's called. Look at that. So this is that's x over time. And guess what? That's y over time. If we had done sy. And again, the time is coming, the time evolution is from the states evolving in time. So, and again, for the zillionth time, a electron is in a magnetic field, same thing as a proton in an NMR field. And normally I want to say it's pointed up. And what happens is you get a pi pulse, let's call that the x direction. You get what's called a pi halves pulse, drives it in the x direction. Do that. It's in the x direction. Starts out aligned in the x direction at t equals 0. But what happens is, over some amount of time, it can actually go to positive. Over some time later, it's now in the y direction, and then it will go backward, and then later it will, well, that came up surprisingly nice. I'm really happy about that. I wasn't even going to draw this, I just thought of this right now. Okay, again, and by the way, this is a mistake for me to draw it straight up, right? You know I should have drawn it in the cone, I just didn't want it overly complicated. And then when I drew it this way, it's still actually a cone. I don't think you remember that stuff, but anyway. Drive it into the x direction, and it moves around. Well, we just did all that. Other big picture, completely consistent with the uncertainty principle. All these are connected. The uncertainty principle is also making this happen. When you start with this state, and you have a lot of information about it, which you're allowed to have, because you don't have an uncertainty principle with z and the Hamiltonian, which is also in z. There's no uncertainty. Everything is in z, everything is known. But what I did was I drove it into the x direction while maintaining the Hamiltonian in z. Now I have perfect knowledge of its location in x and z. I knew it was up, whatever. I now know it's up in the x direction and the Hamiltonian is in z. The problem is now I know too much. I can't know which way it's pointed in the x direction, yet I do. And that's true, but instantaneously it moves out of the way. And by the way, it could also, so I did this, but it could have done that. It's really doing this. And I don't know which one it is. And I'm sure one does this, another does that. And the frequencies won't be perfect. You see, it destroys my knowledge almost immediately. But what you can do, using like ion cyclotron resonance and all this NMR, EPR jazz, you can actually measure that rotation. In a magnetic, in a copper coil, that electron spinning around is detectable. It induces a current inside the coil. And outside of here is a measuring device that sees that current, amplifies the hell out of it. The NMR, right, NMR is a magnet, but there's a cabinet right next to it. It's as big as the NMR. That's the amplifier. It's as expensive as the magnet itself. They're about $1 million. Each one's about $1 million. So, and it can blow itself up too. A lot of the electronics are to make sure it doesn't destroy itself. So anyway, so that's how it works. Okay, last bit, let me tell you where we're going, because I have 1 minute, and again, I'm trying not to, chew up time. I've been terrible about that. Okay, so that's really it on Schrodinger, and for reasons I don't understand, the book says that, oh, we know that the Schrodinger equation doesn't make sense. I don't know what the heck that guy is talking about. This makes perfect sense. The damn thing, the state evolves in time. I get that. The measurement does not. I mean, this is exactly what reality is. I have no idea why the guy thinks this. Regardless, we are going to take a different stance. Now, I'm going to write the same thing, but I'm not putting little bras and kets on it, right? Because the bras and kets are what's evolving in time. I'm not going to do that. I'm going to say that the operator evolves in time. Notice again, no bra or ket is necessary in this approach. This is called the Heisenberg approach. Now we all know that I'm going to write a bra. The bra evolves in time with this. Right? Remember I told you I just didn't put them in here. I just didn't put it in here. It's just at this point you should know what I'm talking about. No bra, no ket. I'm just doing the operator. So therefore, what I'm doing is this operator is evolving in time. The states will not. So I can either have a bra and a ket and let those evolve in time. Here, I can go ahead and do it now. It's not that big a deal. I can either allow the bra and ket to evolve in time, and that's the Schrodinger picture, or I can allow the operator to evolve in time, which is the Heisenberg picture, or frame, or whatever that is. Anyway,
That's how.
huh?
What's
The
the
T.
T?
Right, we're revolving in time. So next time, what we're going to do, and look, you've done a lot of this. You've done matrix times matrix times matrix. You've done that. You've seen, albeit on the exam, that you can make this a matrix. We're not going to do it that way, by the way. But hopefully the concept doesn't blow your mind, that we can actually make the operator evolve in time and not the states. And for reasons, again, I mentioned to you before, this is how it's done. I don't quite get it, but this is how we do quantum time-dependent quantum mechanics. So we're going to cover that next time. And that's the part, again, that is actually that's the difficult part. We'll spend the rest of the week on it, then you'll never see it again until we cover it again a week later. Anyway.